Good morning and welcome to Northeastern. Um, I, I've been on this campus for 23 years, so it's been transforming. This building was built just a few years ago, and since I came here, this campus, before this building was built, there was 13 new buildings built on campus, and you see a new building right there. So it's very dynamic and a very happening campus. So let me talk to you about a project that's been developed at Northeastern, technology that was developed through an NSF center, NSF Nanoscale Science and Engineering Center for High Rate Nanomanufacturing. That's where the technology was developed. It's an additive manufacturing. So I'm gonna first talk about give you a brief introduction, then talk about the technology. We developed a directed assembly of nano elements technology. And I'm going to talk about two of those directed assembly techniques, but I'm going to give you a reference to look at. We did just a review paper last year that covers a lot of the directed assembly techniques, the one we developed, the one that others developed, with a focus on the making of nanoscale devices. Then I'm going to talk about applications in advanced packaging. This is our focus at this point. And I'm going to talk about printing metal resistors, printing dielectrics, and making capacitors and other applications, and then printing of semiconductors and making devices, whether it's transistors, diodes, or logic. And then I'm going to talk about the concept of putting all this technology in one tool. So we call it the fab in a box. So everything is in that fab in a box that we have actually on the other campus in Burlington. That some of you are welcome to visit if you have time. So a note about NanoOps. It's a spin out from Northeastern, and we licensed 35 patents. 23 are issued and 12 are pending from Northeastern, and the technology has been developed over 10 years, involved about 130 researchers. And right now the company has investment from Analog Devices. We have projects with DARPA and NextFlex, and we also work with DoD primes. And also we just have a tool that's been installed in FlexRD in the United Kingdom. So the first tool has been installed. We're negotiating other tools as well. So our focus at this point is on advanced packaging and heterogeneous integration. And it's really more on the new chiplet approach that some of you probably most of you are familiar with. And this is going from big monolithic chips to actually assembling individual chips such as GPU, CPU, memory, and so forth on a silicon interposer or other types of interposer. It could be organic, it could be glass, and so forth. So the problem with these is that the resolution requirement for these new chiplets, for example, is very, very small. They're 2 micron or sub-micron. And it's beyond the capability of the advanced packaging companies, such as Amcor and ASE and so forth. And so we looked at our technology. Our focus was on flexible electronics made using graphene, nanotubes, quantum dots, and so forth. And we looked at this technology and seems to be a very good candidate for what we do. And so basically, and so we started working on it. But just going back, the problem that we wanted to solve is the fact that because these new chiplet approaches with the fine resolution and with the fine pitch cannot be done by traditional packaging houses, it had to be done in a fab. So the only companies that are doing it are Samsung, Intel, TSMC, and others. And so that makes it very expensive. That makes it also very long lead time, as well as no on-demand capability, which is available if you have some of the packaging in-house, for example. And so also it allows it makes it difficult to do other things such as thermal management and other things. Okay, so imagine if you can make your chip or package devices in one day on one machine, and at 100 times less cost than it usually costs you, and with a 25 times smaller carbon footprint. And actually, this technology allows you to do that. And so basically, this is what the machine looks like. It's in our Burlington campus, where we have 25 startups on campus, and basically the it's all liquid based. So all using is liquid. There's no vacuum. There's no chemical reaction, and there's no etching. And feature size, I'll show you, can be done down to 20 nanometers. We do use lithography. That's how we can go down to submicron and to nanoscale. And the reduction in material used is about 1,000 times. It's about 10 to 100 times cheaper. It's about 10 to 100 times faster than conventional fabrication, for example. And it's about 1,000 times faster than typical inkjet or 3D printing techniques. In other words, you can do 1 layer per minute on a 4-inch wafer. For an 8-inch wafer, it will take about 2 minutes. So this is the first technique. This is, we call it the electrophoretic assembly, directed assembly platform. And this one takes about, for a 4-inch wafer, it takes about less than a minute. And here you can see these are gold, for example. Basically you will have vias made in whatever material you have, whether it's a polymer, silicon dioxide, whatever it is that you're using, high K. And then you do the assembly. You need a suspension of nanoscale particles. In this case, it's gold particles. But you can see that we've used copper, we use aluminum, we've used tungsten, we've used a variety of other materials. You can also use the electric, you can use semiconductor. And typically aqueous solution is the best, but you can also use other suspensions. So the question is, for this particular one, by the way, the sintering is not needed because the particles are small enough, the surface forces are large, and as a result, the sintering happens in situ. By the time you finish assembly, it's all centered. So the question was, well, is it completely a solid film? Is it, do we have any voids? What kind of, is it amorphous? Is it polycrystalline? And so we looked at that issue. You can see here that the previous slide shows 50 nanometers. You can see you can go to 80, you can go to 2 micron, and you can go down to 25 nanometers as well. When we looked at took a TM cross section, and it looks like there's 1 grain boundary, and it's a polycrystalline structure. So the question then becomes, well, how does it compare to electroplated, for example, pillars the same size? And so you can see that on the left side here. You can see the first one is the nanoparticle based, and you can see that they're pretty much the resistance measured over about 100 pillars inside an SEM. It gives you pretty much the same value. Now, this requires that you have it's electrophoretic, so you require that you have a conducting surface at the bottom of the via. Sometimes you don't have that. Sometimes you want to put it on any surface. And so in this case, we developed another technique that I'm going to talk about in a minute. Another development that we had, which was just published a year ago, we did a directed assembly technique using silver nanoparticles. In this case, basically on the top here, all the pillars were single crystal. And this was done also in about a couple of minutes over wafer level. In a semiconductor, for example, so the interesting thing is that if the particles are small enough, and small enough meaning 10 nanometer or smaller for metal, and 20 nanometer or smaller for the electric or semiconductor, they fuse on their own. If they are larger, in many cases you can't get small enough, you have to use centering temperature. So in this case, we have zinc oxide, a 2,6 semiconductor, and these, in this case, the particles are 50 nanometers to 100 nanometers. And in this case, we use RTP to applied 1,000 degrees for 2 minutes. And in this case, we get a single crystal also. So you can get single crystal basically using sintering, or if the particles are small enough, you can certainly get a single crystal without sintering. Okay. So what happens if you want to do a large area very fast and you don't really have any conductor to apply electric feed like we did in the first technique? So this is a fast fluidic assembly, and this one you apply photoresist, and then you functionalize. You remove the photoresist. You apply functionalization. So you do hydrophobic, hydrophilic, and then you remove the photoresist, and then you actually do something similar to a dip coating process. And this process takes about a minute. And then you can end up with metal or dielectric or semiconductor pattern the way you want it, whether it's submicron, nano, or micro scale. And so you see some of these examples. Now, this directed assembly is very wide topic. And so we published a paper, excuse me, last year. And the paper was focused on directed assembly that was done by hundreds of people, but with the focus of making nano devices. So if you're interested in directed assembly, we just published a review article on that. Okay, so let's talk about three things. How do you print the metal? What kind of property you get? How do you print the electric? And then how do you print the semiconductor? These are examples of printed metal. So here you can see copper, gold, platinum, and these are for a sensor board that's made for NASA, and these sensor boards go on the ISS, and you can see that the even though it's printed, even though it's liquid, we have a pretty good control over the uniformity, and these are so the uniformity you can see in the profile there. It looks pretty good. So when we worked with a company in San Jose, a new company that makes IoT chips, they had a very small feature size fan out pattern where the pads, the internal pads here, are basically, in this case, they're 40 micron, and in some cases they're 20, in some cases they're smaller. And so they had a really tough time getting any, first of all, the wire bonding was out of the question, but they also had difficulty actually making it. And so they asked us to print it. So we printed it, and then they wanted to compare that. We printed silver. I'll talk about more of the printing, traditional printing ink that's available later on. But this is silver printing. And then they wanted to compare that to copper. So we compared the same exact pattern using sputtered copper. And you can see the performance is pretty close. These are the same thickness and the same pattern. So that gave them confidence to move forward with the printed pattern, for example. This is another one that was from NextFlex, pattern from NextFlex also, that shows the capability of printing. This printing, again, takes about a minute over a 4-inch substrate. This is a pattern from Foxconn, which makes the iPhone. And this pattern, the grid pattern there, this is the same grid pattern touch display on your iPhone, which is 2 micron line width and 100 micron spacing. And they wanted us to do fully printed silver, which we did. And so the IV curve looks pretty good compared to what they have. And what they use sputtered copper on a PET substrate on the iPhone. And we compared the transmittance of light for the PET without the printed silver and with it, and you can see it went down by about just 4%. So that's pretty good. And then they said, how can you print nanoscale so that it would be smaller than the wavelength of visible light, and so that you don't see the screen door effect, for example, when you look at that. And so we did that, and we made line width of about 300 nanometers. You can see here, close up, and the line roughness, the edge roughness is pretty good for that application as well. Okay, so this is a project for with the Air Force, and this is a fully printed passive components. So in this case, we wanted to print resistors. So the first step we did is we used the resistor ink that you can buy from a lot of the ink vendors for inkjet and so forth. So we started with that, and then we ran into a problem right away because the ink basically is carbon black, pretty much, with some ceramics, and so basically it was the tolerance was very, very large. So you cannot print devices that are repeatable. You cannot print devices, and the devices have different resistance. So we moved on to using a thin film resistor, and that worked out very well for us. We got a very good repeatability, very low tolerance, and we can choose the pattern, we can choose the thickness, and print the resistors, whether you're doing 100K or 1000K or sorry, 1000 ohms or 800 ohms or whatever it is, and that gave us good repeatability and good tolerance. Then the next step is to make fully printed capacitors. and fully printed capacitor using inorganic dielectric, not organic dielectric. And so in this case, the first thing we wanted to do is how can we print inorganic dielectric? So in this case, this is alumina, and you can see that we made a lot of patterns here just to test how can we made a variety of shapes and thicknesses and so forth. And so this is alumina. The first thing was the dielectric constant was very good. In this case, 7.2, comparable to vacuum deposited dielectrics. And then we tried to look at when you do dielectrics, a lot of times you do densifying the dielectric to get a very high quality. So actually, this was possible as well here. So here, for example, this is without. This is low temperature, by the way. The metal and the dielectric are both centered at low temperature, 250 or less, which makes it very good for flexible electronics as well. I'm going to show some examples of that. So in this case, basically, you can densify it. That means reducing the thickness of the dielectric layer by heating it at 200 degrees, and that gives you a very good quality with the same dielectric constant. Okay, so what about how does it differ from ALD deposited dielectric, alumina, for example? So we went and we did an XPS and compared the printed one on the left side. This is printed additively and photo annealed, like you saw in the previous slide, with the ALD. So it looks pretty comparable. The properties look very good. The cross section shows amorphous structure, void free, which is very, very important. So that made us happy with the material that we printed. So then we move on to printing the capacitors. These are the capacitors that we made. Typically, in each sample, we have about 640, and we made a variety of sizes from 20 by 20 micron by 20 micron capacitor to 5,000 by 5,000 micron capacitors. We use mostly metal, silver metal here, and we use dielectric, alumina, silicon dioxide, as well as hafnium dioxide, all done in the same way. And you can see and we also did it on polymer. You can see in the corner there. The substrate in this case is parylene. Okay, so then we made it and we measured it. So measured the capacitance, and the dissipation factor was pretty good, and the capacitance was good. And I'll talk about the yield in a minute, and the tolerance. And so when you do the capacitance, a lot of the applications the Air Force is interested in is high frequency, although not as high as our capability. But we tested these capacitance at up to megahertz, and it behaves the same way that we expect it to behave. So this one, for example, you can see this 1,000 by 1,000 micron. These are the pads for the full probe measurements. And then on top of that is the 20 micron by 20 micron. You can see how tiny it is compared to the pads. The pads are the same size in both pictures. So what about yield? Well, all this is done this is done in a lab. There's no clean environment. There's no cleaner done inside the fab. And in this case, what we have done is we looked at this is 18 capacitors that were done. There was no shorts. And these are 500 micron by 500 micron. And what we're looking for is the results, the average about 34 picofarad. And we looked at the ones, our yield was based on the ones that did not meet the spec, which means it's overload, which means higher than 34 that we're looking for, and the ones that became lower. And so the yield is about 66%. This is not optimized at all, and but also the tolerance for those was very, very low. It's less than 3%. Okay, so now we looked at the capacitance and the capacitors. What about printed semiconductors and transistors? This is recent development. So we started with something that's easy to get, easy to obtain. By the way, if you want to print 3.5 semiconductors, it's very, very hard to get nanoparticles. You have to make your own nanoparticles, for example, like indium phosphide, which we did. And to get GaN particles, you get large GaN particles because what they take they prepare them by taking GaN wafers and grinding them and going through ball milling and so forth. So the zinc oxide was easy to get source wise. So but it needed annealing at high temperature. So in this picture here, you can see these particles are about 50 to 100 nanometers. At 800 C, they're still particles. When you go to 1000 C, then you can get a solid film, a form. And so these transistors are done on a wafer, and these are about 37,000 transistors. So they're all discrete, not connected. And so, but they vary in size from 100 nanometers for the channel to 2 micron, and for the length of the channel from 100 nanometers to 20 micron. And so we were very happy with the. This was published recently, and we had a good on-off ratio, for example, for those. And we have an automated probe station, so we can actually test a large number of those. Now, zinc oxide is good, but it's used in a very few applications, some display application, but it's not widely used. So we wanted to do silicon. So this is the silicon, fully printed silicon transistors that we made. In this case, the silicon was the substrate was silicon, and in this case, we printed the electric, the metal, but that's not enough. You need to dope, and doping was actually more challenging than printing, because with doping, you use a liquid dopant, and so you have to tune the depth of the dopant penetration into the substrate, and you have to control the concentration profile of the dopant. So this was done actually here. Let me see if I can get. There's a video here. So this is is it up on it? Can I have the mouse? Okay. So this is a time flight SIMS, and shows the penetration of the phosphorus into the silicon, and shows the profile. And this took a lot because we don't have a time flight sim, so we have to send it out. So we use a lot of modeling, a lot of optimization to do that. And again, it took about 1,000 degrees and about a couple of minutes to do that, but it had to be controlled precisely. Now, once you do a transistor, you can go on and do logic. And so we've shown that you can do NAND, you can do AND, inverters, and NOR, and so forth. So that means that you can actually do, all you need is the ink, the suspension, use this technology. You need RTP process, fast sintering, and then you can actually make your own devices. And you can make devices that have transistors up to 100,000 or maybe a few 100,000 transistors on the same substrate. Okay, so basically this is a list of the materials that we have done. You can see we've done a lot of material in terms of metal, silver, copper, gold, platinum. We've done semiconductors. We've done 3-5 semiconductor. We've done 2-6 semiconductors. And then the electric, we focus on the three dielectrics that we talked about, which is high K and low K. And then the dopants, we boron and phosphorus. So the idea is to go for the chiplet approach, go from monolithic to the chiplet, but by using fully additive. So the only thing you need to bond is the chip, to bond the chip on the interposer that will have a trace, will have interconnect, will have passive components, will have active components. And all you need to add is just add your chips. And this includes submicron. So the tool that we make actually includes submicron lithography. So the tool comes with everything. So all you have to do is just submit your GDS file or DXF file, put the ink, put your substrate, whether your substrate is sapphire, glass, silicon, whatever it is, or even organic substrate, and then the machine will take over. And so this shows a quick video There is a YouTube channel for NanoOps, so you can take a look at some of the videos. But the idea is to have high throughput, have minimum feature size. The tool does not come with 20 nanometers, but it can go down to option 300 nanometers, for example. You can definitely use any materials you want. I mean, I talked about traditional electronic materials, but we've used carbon nanotubes, we use graphene, we use quantum dots, we use organic semiconductors and so forth. And so to summarize, we have demonstrated this project was funded by agencies, companies, and so forth. We demonstrated that you can do fully additive passive components as well as active components. The feature size can be demonstrated, can be done very, very small. You can certainly have a significant reduction in cost and very high throughput. And at the end, I'm just going to acknowledge some of the companies and the agencies that funded us. And basically, it allows you to do advanced packaging on demand or even chips on demand. It's secure for those interested in security. Nobody knows your design. No one knows your material or your substrate. You can do thermal management. We develop thermal management can be done very easily using this technology. And of course, it is sustainable and allows material innovation because you can use whatever material, even the ones that I didn't talk about here. I mean, if you use organic or carbon nanotubes, there's no need for centering. It's ready after you finish. So I'll stop here and answer any questions you may have.
Thank you.